Hello everyone, I'm Adrien Thibaud and I'm a PhD student in the University of Toulouse. I work on congestion control in named data networking, and today I will speak about our proposition, which name is cooperative congestion control. In our study, we work with named data networking architecture, which is a content-based network layer. It offers multiple opportunities such as multi-source and multipath retrieving, which we will focus during this presentation. So the problem we address here is the multi-flow fair distribution problem. This means that we have a lot of flows to distribute in our network and in a fair way. We see that as a joint congestion and fairness problem. Here are the outlines of our presentation. I will now present you the modelization we made. Then I will present you our proposition, cooperative congestion control, and the evaluations. Finally, I conclude the talk and present some perspectives. Our modelization is divided into optimization problems. The first one is a common multi-commodity flow problem, which tries to maximize the use of the network. Here, the Fk are the global rate the user K gets, and it has to follow the constraints 2 and 3. Equation 2 represents the conservation of the flow on each node, and equation 3 represents the respect of the capacity on each link. We add a new constraint to the multi-commodity flow problem because we suppose our users specify explicitly the objectives they target. As a consequence, our solution will not give more than the user wants. This is modelized by equation 4. We solve this optimization problem and we find the solution as Z star, which represents the maximum use of the network. Now we want to ensure that the distribution is fair. So we define a new optimization problem using the max-min fairness. We try to maximize T, which represents the minimum of each flow through equation 6. And we will use equation 2, 3, and 4 as constraints, and the solution we find as constraint also. The solution of this new optimization problem gives us one fair distribution and the optimal minimum each flow should have. Let's try it on this small topology as an example. There are two consumers, A and B, that wants to reach different data through producers A1 and A2 for consumer A and through producer B for consumer B. The first optimization problem gives us that the network can be used at 100 megabytes per second at maximum. And the second optimization problem says that each flow should get at least 50 megabytes per second in order for the distribution to be fair. Now I'll present you our solution, cooperative congestion control. It is a per node approach. This is why we will focus only on one node. But here is a global picture where we have one consumer that tries to retrieve the data from n producers. Our solution is pace-based. That means that we will work on the pace of the interest through our multiple algorithms. In the upstream, the consumer will send the interest at the pace pi, and on the other side, the downstream, the data will be sent hopefully at the same pace that the interests are received by the producer. We define our solution as a framework with generic rules and based on three main principles. Multiple implementation can be imagined, but we first try to keep it simple in order to evaluate the concept. Our first principle is that there will be cooperation between nodes. The second principle is that each node will locally detect if a congestion is occurring. Finally, the third principle is that, based on the information get from the cooperation and the local detection, each node will allocate smartly the flow using their multiple paths. The first part of the cooperation are the objective I spoke about earlier. The consumer will express the objective in terms of pace it wants to get. The node will receive one objective for each flow and will have to distribute it among its multiple subpaths. There is one algorithm that has to do so, and the only rule here it has to respect is the one called conservation of the objective, as described by the equation 7. It means that no objective is created in the network. The node gets one objective and splits it among the output path. At a global scale, the objective that is sent by the consumer is equal to the sum of those received by the producers. The second part of the cooperation are modeled by constraints that are carried in the downstream. The node receives a constraint for each of its paths, and it has to aggregate the constraints for the asking interface. Thus, the outgoing constraint cannot be higher than the sum of the incoming constraints. But it can be less than that because of local congestion problem that I will explain next. This is why equation 8, which represents the aggregation of the constraints, is not an equality, but an inequality here. For our second principle, the local congestion detection, we choose to use active queue management for our first implementation. But as CCC is a framework, you can use any algorithm you want to detect the congestion. Our last principle, the entire flow smart allocation using multiple paths, can be divided in several algorithms. The first one I will present is how to react to local congestion. Congestion occurs when multiple flows use more bandwidth than the link is able to handle. So the node has to reduce all active flow by reducing their outgoing constraint. The reverse algorithm is how to react when there is unused bandwidth on the link. That can occur when you overreact in the first algorithm, or when a flow ends and leaves a part of the bandwidth unused. Here we want to distribute the bandwidth among all unsatisfied flow and increase their respective outgoing constraints. An unsatisfied flow is a flow whose the incoming objective is lower than the outgoing constraint. Here, equation 9 says that we increase the outgoing constraint by a fair share, but that it is still maximized by the sum of the incoming constraint, in order to respect the previous aggregation of the constraint. It means that an increase of the outgoing constraint is bound by the capacity of all the subpaths. Finally, we have to determine how we load balance the traffic, because we receive a lot of information, such as the constraints and objectives, but we never specify how we use it explicitly. The only rule is that for each subpath, the effective pace should not be above the received constraint, as equation 10 says. So here is a figure that summarizes all the concepts I explained in this presentation. For the evaluation, we use the topology I presented you for the modelization example. We compare our solution with the optimal solution found in this section and with two couple of existing solutions that we choose in our previous paper. They both combine an end-to-end congestion control solution and a forwarding strategy to use multiple paths. We use ND and SIM to conduct our simulation. The consumer A begins at t equal 0 seconds, while consumer B begins at t equal 10 seconds. Thus, at 10 seconds, both flows cohabit and use the network concurrently. We can see that our solution and the state-of-the-art solutions are not fair in comparison to the optimal solution found in the modelization. What we can say is that they are fair on a link level. Indeed, they share fairly the bandwidth of the congested link, which is the one between the node R1 and the node R3. But they are not fair at a network level or at a global scale. Our solution here does not improve this aspect in comparison of the state-of-the-art solutions. But we see that it is more stable than the other solutions and thus reduces the completion time of the download for both our consumer. In addition to all that, we can see that our solution has a fast convergence phase when flow begins or ends. In conclusion, cooperative congestion control is a framework based on three main principles that can be implemented through 6 modulable algorithms. Our first implementation successfully used the multipass capacity of named data networking and can achieve the maximum use of the network. But it has some flaws as it only achieves links level fairness. One of the perspectives is quite clear and is how to reach the network level fairness. On a global scale, we plan to define more complex algorithms in order to have even better performances. And one point that you might have noticed is that we only consider one incoming interfaces for the interest when there can be multiple. Thus, we plan to add this feature in our algorithm in the near future. Thank you for watching my video, and I'll be pleased to answer your question.